Hello, in this video we're going to talk about enzyme kinetics. So first up, what is an enzyme? So an enzyme is a biological catalyst, and we haven't really talked about catalysts yet, but a catalyst is a thing that makes your reaction go faster, but is not overall consumed in the reaction itself. It plays a role in the reaction, but then it's regenerated when it's done. Okay, so then enzymes are biological catalysts, and usually they're large proteins, but they can also be RNA. And they're remarkably effective and specific to certain molecules. So this enzyme is going to work really well, and it's only going to work on these few substrates. And so the picture we have here is of glucose, which in this case is the substrate, and that finds its way into the active site on the enzyme, which is hexokinase. And then the structure of the enzyme changes a little bit to kind of fold around the substrate, and then it catalyzes the reaction very efficiently, and then it releases the product, whatever that is. In this case, glucose 6-phosphate. All right, so then how do we describe the kinetics of this process? It's a really important process biologically, biochemically, etc. We want to study it. How do we do kinetics on this? And so the simplest way to do this is something called the Michaelis-Menten mechanism, where you start with a substrate and an enzyme, and okay, they'll come together. That's the first step, right? They have to make a complex. The substrate has to find its way into the enzyme. And then from there, it may come back apart again, like maybe the substrate leaves the enzyme before the reaction occurs. And so this happens pretty typically, right? The substrate enzyme goes in and out, in and out, in and out. And then at some point, the substrate in the enzyme will do its reaction, catalyzed by the enzyme, and then your enzyme will release products. And so in this case, I'm showing it as products are two parts, like it's breaking something apart, but it doesn't have to do that. Oftentimes these reactions will put two things together or modify one thing, something like that. Now we have our kinetics on the top here. So the enzyme plus substrate is the reactant of the first step here, and then that's in fast equilibrium with the enzyme substrate complex. So there's both a forward and a reverse reaction here because they come together, fall apart, etc. Then there's a second step in this mechanism where this enzyme substrate complex makes products. So ES is this enzyme substrate complex, E is the enzyme, S is the substrate, products, okay. Now something interesting about enzyme kinetics is that sometimes it's a first order reaction, sometimes it's a zero order reaction. It just kind of depends on what the concentration of substrate is relative to the enzyme. So at a really low concentration, it's this first order in substrate. You add more substrate, your reaction rate increases because, well, there's a bunch of enzymes sitting around waiting to do something, and so more substrate will get reacted faster. Now, when you have a lot of substrate relative to enzyme, you wind up saturating the enzyme, it's called, and so then you add more substrate and then nothing happens because all the enzymes are full. So if you add more substrate, nothing else is going to happen. It's like if you have a gas station and all the pumps are full and then there's a big line out the back of more people waiting to get gas, that doesn't really increase the rate at which the gas is transferred because all the pumps are full, right? So the same thing happens here. All right, so let's dig into this kinetics a little more. So if we look at this, all right, the first step is usually faster, but not always. And so that winds up tweaking what we do here compared to fast equilibrium steps that we talked about in the previous video. And so, all right, so this first step's usually faster. The second step's usually slower. So if we were to look at this from what we know, all right, the rate is equal to the constant times the concentration of enzyme substrate complex because that's the reactant in the slow step, right? Now, the problem here is ES is an intermediate, and we can't use this in the rate law. So we got some work to do, right? And if the first step was much faster, well, then we could do just like we did before, but the first step's not always faster, so we have to do something else instead. And what we do is we assume that this total concentration of enzyme substrate complex is constant. So this is called a steady state approximation, and we call it this because we're assuming that the ES concentration is steady during the reaction. And this is actually not a bad assumption for enzyme kinetics because if you have a lot more substrate than enzyme, then it's going to form some, constant amount of complex. Which is probably going to be most of the total enzyme concentration. And this is actually kind of typical for enzyme catalyzed reactions, especially when you study them in the lab. And so, cool, that makes sense. So we can talk about, from our first step, the rate of the enzyme substrate complex formation, because that depends on the reactants here going forward. And then we can also talk about the rate of breakdown for the enzyme substrate complex. And so that's the ES concentration and the K1 for this reverse, right? So it's the reverse reaction here, what that rate law would look like, right? So that's that part. And then there's also this other way to get rid of the enzyme substrate complex, which is to send it forward through the second step, right? And so that's here. Now, the second step is usually slower, but not always, right? If the second step was always slower, then this is small compared to this, so we can just kind of ignore the second bit. And then we're doing just like we did in the last video. But because the second step's not always slower, we do need to include both of these, which then tweaks how our outcome is from the kinetic consideration. And so you can combine these two constants together if you want. That makes a lot of sense to do it that way. Now, since the enzyme substrate concentration is constant, we can say that the rate of making it is equal to the rate of breaking it down. And so when you make it, all right, that's the first step forward. When you break it down, that's both the first step backwards and the second step forward. So we can set these equations up like this. All right, so let me move this up. So, just like we did before, we can solve for this intermediate, the enzyme substrate complex, and then use that to eventually plug this into the reaction. But we have some work to do first. Okay, so here's another way to write this. First, we'll combine all these constants together into Km. And so K subscript m is the Michaelis-Menten constant, and it represents something. It represents the measure of the substrate's affinity for the enzyme, i.e. how much do they like to stick together. And so it's an inverse equilibrium constant, and we'll talk about equilibrium constants later, in that a small Km indicates they stick together a lot, and a large Km indicates that this binding process is not as favorable. Km does have units of concentration, because it's an inverse equilibrium constant, and oftentimes equilibrium constants have, inverse concentration units. And, all right, so then in a table on the right, we have some examples of what values of this will look like, and they vary widely. It depends on the enzyme and the substrate and all these kinds of things. But we do use Km as one of the things that we can talk about when we're talking about enzyme-catalyzed reactions. All right, let me scoot this up. So now that's the first thing. We replace these constants with Km. The next thing we have to do is that we don't know the free enzyme concentration because, well, some of it's the complex, some of it's not. And all we know is how much enzyme was in there in the first place. And so we use this equation that, well, okay, the total enzyme concentration is equal to enzyme free plus the enzyme bound. All right. And then we can solve this equation for concentration of enzyme, and then we can plug that into here, right? So this will solve for this, and then we'll plug it up into here. And then you do that, you rearrange some things, and then you get this form of the equation like this. All right. Now, we have our revised form of what the enzyme substrate complex is in terms of the rate equation, and then we can just plug it up in here into the overall rate equation for our mechanism that we looked at, because we assume the second step is slower, and we get this equation. All right, we're almost there. The last thing we're going to do is we're going to define a maximum possible rate. And so the maximum rate is when you have the highest substrate concentration, because remember our plot we looked at originally, the y-axis value, which was rate, got highest all the way on the right side, which is highest substrate concentration. And so, all right, if the substrate concentration is really high, then essentially all of your enzyme is bound up as that enzyme substrate complex. And so we can assume that E total, enzyme concentration total, is about equal to the enzyme substrate concentration. And then we can make a little thing like here. Okay, the maximum rate is from the second step, and it's equal to Ks times the total enzyme concentration. That said, you're not always at the maximum, right? So we kind of wind up treating Rmax like a constant. If this was maxed out, what would your rate be? And then realize that we're not always maxed out. So now we take this Rmax and plug it into the equation we had. So K2 enzyme total, K2 enzyme total. So we plug this in right over here. And then now we finally have our Michaelis-Menten kinetics equation down here in the bottom right. So this is it. Ta-da! Great. So now let's talk about this a little more. So again, here's the plot. Now, we can label this a little more, right? Rmax is the highest rate you're going to get at the maximum substrate concentration. And then it turns out that at the concentration equal to this binding constant, your rate is going at half the rate of Rmax. Okay. And then remember, Km represents strength of enzyme substrate binding. Smaller Km, bigger binding. K2 is a rate constant of the second step, which can be also called Kcat, the catalysis rate constant. And then Rmax, sometimes known as Vmax in other versions of this formula, that's equal to the maximum rate. Okay, so something else that's we should think about. Earlier I said that at low substrate concentration, this reaction is first order. So let's see if that's true. So low substrate concentration, that would say that in the denominator here of the equation in the green box at the top, your substrate concentration is really low compared to Km. So you can ignore that. It doesn't mathematically play much of an effect. All right, so let's rewrite this with that S out of here. Well, now we just have constants over here on the left, so rate is equal to some constants times the substrate concentration to the first power. Great, that's first order at low substrate concentration. Then we also said at high substrate concentration, it's zero order. So at high substrate concentration, the Km is now really small compared to the S. And then, all right, we can rewrite that, take the Km out of there, and hey, now our S's cancel. Check that out. And so then we have rate is equal to just Rmax, irrespective of substrate concentration, and that's a zero order reaction. Great, so our boundary conditions make sense compared to what we think they should be, and this whole kinetics kind of formalism works out pretty well. So now the things we want to know when we do enzyme kinetics is we want to know what these values are, Km, K2, or Kcat, and Rmax. We typically don't, I would never do this, ask you on a test to derive the Michaelis-Menten equation, because that's something, it's just not fair to ask you to do that. But we can ask you to figure out what these parameters are and kind of work with this equation and understand what the pieces are. Okay, so we're going to want to figure this out, and generally what you do is you measure the rate at a variety of different substrate concentrations, and then you can plot that and fit it to this equation to solve for Rmax and Km. Now, that said, fitting a non-linear equation can be pretty difficult. There's computer programs that do it no problem, but generally Excel needs a straight line. The spreadsheet programs need a straight line. So we take this rate equation and turn it into a linear form simply because we can fit it better, not because it is intellectually any more pure. And if anything, I think it's less pure intellectually because we're just messing with it to make it a straight line. So this is called the Lineweaver-Burke equation if you do it this way. And hey, it's equal to y equals mx plus b. So y is your inverse rate, x is your inverse substrate concentration, then your slope is equal to Km divided by Rmax, and the y-intercept is equal to 1 over Rmax. Now, what you can do is you can go plot it, and when you plot this, you take your intercept and say, hey, look, my intercept value is 1 over Rmax, so then you can solve for Rmax. Once you do that, you can then look at your slope and say, hey, this is Km over Rmax. You just found out what Rmax is, so you can solve for Km. And then from there, you can use this equation that Rmax is equal to K2 times the total enzyme concentration to solve for what K2 is. So let's practice that. And the enzyme fumarase, it catalyzes this conversion of fumarate to malate. This is part of the citric acid cycle, or the Krebs cycle, which is a very kind of central method by which your body takes food and turns it into energy. And so, all right, let's look at this step here. So using these values, determine the various parts of the Michaelis-Menten kinetics formalism here. Okay, so we have our data where we measured the concentration of substrate, in this case fumarate, and then measured what the rate is at each of those concentration values. And so we're going to use our equations here, right? So this is the equation that describes the kinetics, but we'll use the linear version because it's easier to fit a straight line and play with that. All right, so let's do this. So using the linear version, I'll just calculate what 1 over the substrate concentration is, which is 1 over fumarate, and this will be an inverse micromolar is the units here. And then also take the inverse rate and just put these in a table because we're going to need this information. Now, all right, so here's the inverse pieces. And so the y here is 1 over rate, which is on the right side of the table. X is on the left side of the table, 1 over substrate concentration. Now we got to find what the slope and the intercept are. So the way to do this without a computer is to pick a couple points and find the slope. The slope is rise over run. And so you take, a couple of the rates, subtract them from each other in the inverse form, right? Because remember, we're plotting 1 over rate. And then the run is 1 over substrate concentration. So when you do this, you can solve for the slope value. All right. This is old school, like 9th grade math. It may have been a while, but this is something that you learned how to do a while ago. Then we can find the intercept. You take y equals mx plus b. You just found the slope. You know what y and x are because you can pick a point arbitrarily. And then you can plug these all together and solve for b. So in this case, b comes out to be 0.008. The sig figs get kind of messy here because somewhere in the subtraction, we wind up losing a sig fig. Okay. Now that we have this information, we can then calculate our max, which is 1 over the intercept. Perfect. Again, we lost a sig fig along the way. And by lost a sig fig, I mean this is the right number of sig figs. It's just that in one of the subtraction steps, our 2 sig figs became 1 sig fig. Okay, once we have our max, we can use the fact that slope equals Km over R max and solve for Km. And do it this way, and our Km is 4 micromolar. Great. Now, there's a large chance for error here because we only use 2 points, right? So if there's some experimental noise in these points, then maybe you accidentally picked an outlier for doing this. You have no way of knowing because you just took 2 of the points and went to town. So it's a better way to do it is if you fit this data to a graph. Granted, this is hard to do on paper, easy to do in a computer. And so let's take this data and we'll plot inverse rate versus inverse substrate concentration and fit a straight line to this and then get these values for slope, intercept, out of it, and then the r squared. Now this is fake made up data, so the r squared is 1. In all likelihood, when you measure this experimentally, your r squared is not going to be 1. All right, so then we can do the same thing here. Now we have our max, which comes from the y-intercept, just like before. And then we can find Km, just like before, and get 4 micromolar. Now when you're doing this, the sig figs, I usually assume that the sig figs for the y-axis, so for the intercept, I assume that the sig figs are the same as the y-axis. And the y-axis, most of these are 2 sig figs. So, okay, I'm happy with calling this 2 sig figs for the intercept. And then that gives us a 2 sig fig answer. Now for the x-axis, again, the minimum number of sig figs here is 2. So I'm happy with saying that the slope has 2 sig figs because it's rise over run. Rise has 2 sig figs. Run has 2 sig figs. Great. Then this gives us 2 sig figs out the end. And hey, I'm just happier that if it makes sense because when you fit multiple points to a line, you're going to have a more precise way of getting the answer than if you just take 2 points. So if it just happens that you get more sig figs that way, great. I think that's fine. Okay, so that's what we have about Michaelis-Menten kinetics and how to work these kind of problems. And so definitely take a minute to look through this and think about how to actually use this and get information out of data. And then ask me if you have questions. Thanks for watching.